whole thing's just to be about the fundamental elements or the atomic structure and fundamental portions of the atomic structure, the subatomic particles, and how they how the construction of the atom affects how we produce electrons. Right, so we talk about fundamental elements. We talk about the periodic table and how many elements we have identified. We talk about what the word atom means. We talk about the Greek atom, which was the four essences and four states of being. We talk about the development of the atomic model past that. So the Greeks, that was your four essences. They gave us the word atom, which fundamentally just means uncut. That means something is something until you cut it down a little bit more and it becomes something different, right? So that's the definition of an atom, is the smallest portion of something that you can have, but if you subdivide it any further, it becomes its own thing or two separate. So we use the example of water. You divide water and it becomes hydrogen and oxygen. So we'll talk about the atomic models. So the models that we looked at were the Dalton model, which gave us the hooks and the eyes, which introduced us to the concept of bonding. And we talked about the Thomson atom. The Thomson atom was the plum pudding, and it introduced the electrons on the outside of the nucleus. We talked about the Bohr model, and that's what we use now, and it looks like a miniature solar system where we've got a well-defined nucleus on the inside, which would represent, in the solar system model, the sun, and then the electrons would be the planets revolving around the outside of that. So those were our models that we talked about, and that just kind of wraps this up in a real tight, summary. There are some things to consider about that, though, and that is that the nucleus, the bigger nucleus, then the binding of those electrons inside of those shells is going to be greater, right? So the fatter the nucleus that we have, the more tightly bound our electrons are going to be in place, right? So we've been looking at the solar system model, the Bohr model. We draw two conclusions on electron arrangement and their binding energies. One was the bigger and fatter the nucleus, the stronger the binding energy, but the other one was the closer the electron versus the nucleus, the greater the binding energy, right? So just a video on atomic structure you can watch at your convenience. And then, of course, we know what an ion is. We've been talking about that all semester, and that is just charged particle. Anytime we have an ion, for our purposes, what we're going to be talking about is selective removal or addition of electrons. We're not going to be adding any protons. So in our atomic model, we talked about the subatomic particles. We only had three that we were interested in. That was the neutron, which we were less interested in than the other two. The other two were the proton and the electron, right? So the proton was positive, the electron was negative. They have exactly the same charge, magnitude-wise, just opposite, right? So we talked about the relative size of them. We talked about their location, and the electrons exist in shells. And then in our Bohr model, those again are represented by the planets, right? In our solar system model, they represent the planets. So they're outside of the nucleus, around the outside of the nucleus. The protons were inside the nucleus, and they were compared to the electron as far as size goes. What do we say about them? Huge, right? They're massive. Same with the neutrons. But the neutrons, again, until we get into radioactive decay, they just don't really play a part except for adding size to the nucleus of the atom. So for our purposes, they don't. I won't say they don't matter, but they matter least of the three, right? So they are inside the nucleus, positively charged, so massive in comparison in size to the electron. And what is it that the proton determines? The atomic number. What is the atomic number? Number of protons. So we're going circular here, but what does that tell us about that atom? The number of protons, the number of positive charges inside the nucleus atom tells us what? what the atom's, right? So the neutron certainly adds weight to it, so to speak, adds size to it, but what controls the type of atom that we're looking at is the number of positive charges. So how many positive charges should we have in relationship to negative charges?
Same.
It should have the same, right? Otherwise, we have a charged particle, and we call the charged particle a ion, right? So then we talk about the electron and the arrangement of electrons inside of shells, and there were two significant things about that. You know, aside from the things we already talked about, the closer they are to the nucleus of the atom, the higher the binding energy. So aside from that, what can you say about the electron arrangement?
Outer shells have 8.
Bingo. The outer shell has 8, no more than 8. Can never have any more than 8. It wants to have 8, but it can't have any more than 8. It can have fewer, but it can't have more. So that's number 1. Yeah, okay, that was number 1. I was trying to think of what number 2 was. So we can calculate, though, the number of electrons in any shell using what formula? 2n squared. So when you're calculating that, what's your first step? In order of operation, that's that math that you should have learned in school.
You square it.
Yeah, you gotta get rid of the parentheses first. We don't have parentheses. The second thing is exponents. So we've got to get rid of the exponents, right? And then it's division, multiplication, addition, division. Is the whole gamut of order of operation. So really the only thing then that we have is the exponent, right? And then the multiplication. So if you square the n, if it's the first shell, it's 1, square the 1, you get 1, and then you multiply by 2, so the inner shell you can only have 2 ever, right? 2. And then the next shell would be 2 times 2 squared. So that would be 2 times 2 times 2, right? So, and 8. So anyway, that's your electron arrangement. How do we number the shells? What's the innermost shell? What do we call it? K. Right. So K shell. You may hear it referred to as K edge at some point, but it's K shell, so it's the innermost shell of the electron. Okay, so atomic number again is the number of positive charges, number of protons. It determines what the atom is. The atomic mass number is the entire weight. Classification of atoms. We talk about isotopes. Isotopes were same atom as most important thing in the 4. Isotopes were same atom with a different number of neutrons. Sometimes those neutrons, too many of the neutrons, it becomes radioactive. And if it becomes radioactive, we undergo the radioactive decay either through alpha emission, beta emission, or a combination thereof. All right, so we'll talk about that coming up. So a radionuclide is a radioactive isotope. So a radioactive isotope, we don't use that in diagnostic imaging, but we do use it in nuclear medicine, right? And here's the thing, I'm not sure I really touched on this very much. I think I mentioned that the radioisotopes that we use in nuclear medicine are man-made. And the reason we use man-made is because of the short half-life. And I think I mentioned that some of your isotopes of potassium have hundreds of thousands of years in their half-life, right? Even the shorter, some of the shorter ones, carbon-14 is what we use to radiometric date bones, and it has a half-life of 5,000. So grandma is suspected of having thyroid cancer. You want to inject her with potassium so that she's going to be radioactive for 100,000 years, right? No, you don't. So we're going to inject her with something that has a very short half-life so that it's gone, in a day or something like that. So we use those man-made radioisotopes for that reason, is that they have a very short half-life. And the complication there, this is just kind of a side note for your, for your information, is that if we're receiving those radioisotopes from Dallas, let's say, and they've got to make a trip from Dallas to Tyler so that you can inject grandma at 4 o'clock in the afternoon, they have to be very precise in their creation of these radioisotopes and account for that drive time and the time that it may sit in the lab before it's injected in the grandma. And if the exam is delayed, then they might not get as good an exam as what they otherwise would have. So very precise in the creation and the dosing of that. So we talked about beta emission and alpha emission. Beta emission was essentially kicking out an electron from the nucleus of the atom. And with beta emission, since we take a neutron and we kick an electron out of it, then what do we get from that neutron? What does it become? Proton. So our atomic number goes up. And then if we undergo alpha emission kicks a high helium nucleus out, which is 2 protons and 2 neutrons. So our atomic mass and our atomic number both go down pretty dramatically, right? So then we talk about radioactive half-life, and radioactive half-life again is how long it takes a quantity of radiation to cut itself in half. And that's not saying that your uranium is going to shrink. It's just how radioactive is your uranium, right? So if you have a quantity of any kind of radioactive material and the half-life is 1 hour, then 1 hour, in 1 hour, you're going to have 1/2 of what you originally had. But that original now becomes, or that new quantity now becomes your original. So if you're calculating 2 half-lives, you have to cut that new portion in half, and so on and so forth, right? So there is a question on the test calculating radioactive half-life, and again, I recommend you just draw a circle. Half of that, that's 1 half-life. Half of that, that's another half-life. Half of that, now you're down to about 1/8, right? In three half-lives.
So would you ask it and say like it starts with like 100, and then you like tell us like 1 year's a half-life, how what's going to be in like 2 years?
Right, something similar to that. You're going to have everything except for one component of it. So it'd be like, you've got 100 units of whatever. How many half-lives does it take to get to this? Yeah. Then we'll talk about ionizing radiation. Ionizing radiation was radiation with enough energy to eject an orbital electron and therefore create an ion. And really, you create an ion pair because the free-floating electron also is a charged particle, and therefore it's an ion, right? So it removes an orbital electron. We talked about the different types of ionizing radiation. Particulate radiation, beta emission, and alpha emission, both are ionizing radiation, but they're not electromagnetic. So not all ionizing radiation is electromagnetic, and at the same time, not all forms of electromagnetic radiation are ionizing. Right? So are you being ionized by the fluorescent lights in here right now? The answer is no. But are you being hit by ionizing radiation? I see a few heads nodding.
Maybe 50-50.
50-50. Come on, man, you gotta commit to something.
I know.
Yes, you are.
Okay.
You're getting blasted all the time. 100% of the time, you're getting hit by ionizing radiation. Where are you getting that from?
Light.
Some light, X-rays, certainly, which is invisible light. But you remember talking about the natural and man-made radon. So radon, a large part of your radon, maybe all of the radon, comes from building materials. Take a look around. What are you sitting in?
Building.
Building. What do you think it's made of? Material. Yeah, so it's building material. From the concrete, from the wallboard, you're getting hit all the time. So ionizing radiation all by itself is not necessary. I mean, it's potentially harmful, but you're getting hit by it all the time. Now, does that mean that you need to get hit more by man-made radiation in the hospital? And the answer is no. If you took from that you're getting hit by ionizing radiation all the time to not protect yourself in clinicals, and you totally missed my point, right? Still, you need to protect yourself. You protect yourself three ways. Non-resistant shielding, exactly, right. So, ionizing radiation, we took a couple of rabbit trails there, but that's okay. And photon is the last thing, and photon is really where the next chapter picks up. Photon is a single piece. It's kind of like an atom of light or atom of electromagnetic radiation. So it's a single piece of electromagnetic radiation. We're going to talk about that. I've posted a couple of videos in Canvas that you can watch that kind of discuss exactly what a photon is and what electromagnetic radiation is. And one of them's really pretty fascinating. Well, it's not really fascinating. It's kind of hilarious. You know, this guy's carrying this massive box out to the beach, and he sets it down and he starts interviewing people and asking them what it's like. Think about that question. What is light? Can you give me a one sentence answer? What is light? It's tough, isn't it? It's hard. It's hard to define exactly what it is. And we use it all the time, right? But so much other stuff in forms of radiation collection, we can define a whole lot. I mean, radioactivity, we can define a lot easier than exactly what is light. All we can say is the type of electromagnetic radiation allows us to see, and that's about as clear as you can get with it. So we're going to get rid of this. Any questions on chapter 3? It's chapter 3, right? Before we go on. No. All right. So I'll show you the videos, where the videos are. I think that I saw this. Yeah, they're under double slit experiment. And I'll describe that probably not today, because we're not going to get there yet. But yeah.
Questions or comments?
Let me turn that off. So there's a set of quizzes that I'll give you in sophomore year. And yesterday in class, I got to print off. So I just showed them on the computer, and accidentally got the key before it took. So I'm not going to make this. At least not right now. I will make a mistake.
We wouldn't mind.
What's that?
We wouldn't mind.
You wouldn't mind? "41 questions. 41. And so I may or may not have told you when I write a test, you know, I just write questions until I get to the point where it's like I got nothing else to add, but I don't want to delete any of these. So, you know, if I write a test, it usually comes up with some weird numbers. Also, bonding is on this too. Remember, we've got 2 different types of bonding. I don't know why that's not in the review. We have 2 different types of bonding. Ionic bonding is just sharing of electrons. You know, one atom gives up an electron and becomes an ion. One receives an electron and becomes an ion. Opposites attracting, they come together. It's an easy bonding, right? But the covalent bonding is where you get the attempt to create eight in outer shell, and it's hard to create, hard to destroy. And we use the example of the creation of water in the space shuttle taking off to describe that. So those are 2 different types of bonding. In both cases, you've got sharing of electrons. It's just what is the purpose of sharing of the electrons? In one case, it's to get 8 in the outer shell, that's covalent bonding. And with the ionic bonding, it's just the attempt to not be ionic anymore, but rather to be neutral, right? So you got two ions come together to create a neutral charge.
Are you gonna ask about compounds too?
That's a good question. I'm not 100% sure, so, an element would be, okay, just to make sure that we cover an element would be like an atom, right? And then if we have a combination of atoms like water, now you got a molecule, right? So, a compound is just a collection of molecules. So, it's a compound of water, right? It's just a bunch of water, So, thank you. All right, then now what we're going to talk about is electromagnetic energy, and this is where you should start your studies before the final exams. Okay, so there's an extensive final review in Canvas. It's like 7 pages long or something like that, and it's just questions and answers. And if you read through it, the questions, you'll see them the same question or similar question, different portions of the review. All right, so chapters 1 through 3 were just foundational to get us to this point. When you start studying for the final exam, I really recommend you start reading through that so that while the material is fresh in your mind, you can start answering those questions for yourself. Start with chapter 4. Okay, there's going to be exactly nothing on the final exam from chapters 1 or 2. The only thing in chapter 3 that you're going to find on the final exam, we're going to cover over and over again throughout the semester, and that is, specific to the tungsten atom. Okay, so chapter 4 on is what the final is going to cover. So don't. We get to the end of the semester, don't waste time studying chapter 1 through 3. Right. It wasn't a waste of time to this point, but in your studies for the final exam, it will be. All right, so electromagnetic energy. Electromagnetic energy is a type of energy that we're familiar with, and we use in a lot of different cases: heat, light, microwaves, things like that, and certainly X-rays. And it's a type of energy that exhibits both electric and magnetic properties. Maxwell kind of described that. Even though we can't really detect the electric and the magnetic properties, they're there. All right, so going back to the Greeks gave us the word photon as well as atom. And what they said a photon was a single piece of electromagnetic radiation. So it would make it sound like electromagnetic radiation and light itself is a little piece of matter, right? And we're going to talk about that next week. We'll have a test on Friday. Next week we'll talk about what we refer to as the wave-particle duality of electromagnetic radiation, and whether or not it acts like a wave, whether or not it's a particle, what is it exactly? So we're going to talk about that next week. But the Greeks clearly thought it was a piece. You can break it down to a single piece of something, and they called that piece of something. But it exists on a continuum, and what a continuum is where you've got overlapping things, right? So where you've got indistinguishable blurred lines where you can't really tell one thing from another, you've got a continuum, all right? So there's no real maximum energy to electromagnetic radiation. There's maximum we can detect, and there may be no minimum either. So it's continuous in both directions, and those energy levels overlap. So if you look on page 59, you see a representation of our most common types of electromagnetic radiation. So at the bottom, and it, this may surprise you a little bit, some of these things we use constantly and they look totally different and you might not really recognize that they're the same type of energy, just existing at different energy levels. So radio frequency waves. You watch TV, you listen to radio, you use Bluetooth, and you your earbuds and whatnot. You're using radio frequency waves. It's a type of electromagnetic radiation. It's very low energy electromagnetic radiation, but fundamentally it's the same type of energy as what are X-rays and gamma rays. So we use those, and we got microwaves. How many of y'all cook on a stovetop every time you want to eat? I see no hands, right? And you may cook once and then you microwave it, the reruns for 2 or 3 days, right? So microwave ovens is just a different type of electromagnetic radiation. Infrared. So what does that sound like? What's that?
Red.
Okay, it's red. You go to McDonald's. What's that?
Red light.
Red light,
Like
exactly. That nasty cheeseburger has been sitting under that red light for 6 hours before you buy it. Sitting under that red light to stay warm, right? So infrared radiation gives us heat, right? So we get infrared radiation from the sun, heat from, anywhere that we create heat. And then look at visible light. How much of that spectrum does visible light represent?
Not much.
Not much. And then within that, what we see and what we use mostly is what we refer to as white light. It's white light because it represents all different energy levels within the visible light spectrum. But if we were to take a prism and hold it into the visible light, what do we see?
Rainbow.
Rainbow, exactly. You see rainbow, you see it broken apart. So even within that little bitty range, you see that little box off to the right hand side where you see violet, blue, green, yellow, red. Those are all within the visible light range. And then directly above that, we've got ultraviolet. Right. So this is where I can give you an example of what a continuum kind of is. So what do you get from overexposure to ultraviolet light? Something. Yeah, you get something. Radiation burns. The early stages of radiation burn gives you the exact same appearance as sunburn. Okay, so we don't see radiation burns in the hospital all that much anymore. And usually the only places we do see it is in maybe cardiac catheterization where they're having a hard time opening the arteries and stuff like that. It's even rare there, but once in a blue moon, we actually do see radiation burn in the hospital. And that's why. Is because they're having a hard time opening an artery and they're on fluoro a lot. Okay. So a few years ago, there was a story where somebody got a radiation burn. I think it might have wound up killing them in CT and that was completely the operator's error. Just overexposed the patient over and over and over again until it really burned them up pretty bad. We don't see that in the hospital all that much anymore, but once in a while we do. So the question then becomes, if you look at this, what we consider to be ionizing radiation are just X-rays and gamma rays, right? Are the only two on that chart that are considered to be high enough energy to ionize, remove an orbital electron and ionize. But I would argue, the entire scientific community may disagree with me, that's fine. But I would argue that if ultraviolet radiation gives us the same appearance in the early stages of overexposure as what do radiation burns, might ultraviolet be doing a little ionizing of its own? Potentially, maybe, yeah, perhaps. Okay, so if you know that overexposure to X-ray and gamma rays are bad for you, and if possibly ultraviolet also potentially ionizes, then what should you be doing every day? I'm not saying don't go out in the sun. I spend as much time outside as I can, go to the beach, the whole 9 yards. But if you are going to go outside and you're going to expose your skin to the sun, what should you do? Sunscreen, cover it up. Yeah, whatever you got to do. Just minimize that exposure because at the very least, overexposure does increase your risk of cancer. Also, exposure to X-rays and gamma rays increases your risk of
Cancer? Okay.
yeah, exactly. So, something to consider. So it exists on a continuum. I don't like combining words there. Exists on a continuum where you can't really differentiate at the interface between two. Is tough to identify, and it goes on forever in both directions. All right, so that's what a continuum is. James Clerk Maxwell is who described it. All right, so this is where we're going to spend the bulk of the rest of the day and why I keep this lecture pretty short. All right, so there are four to electromagnetic radiation. All right, so what we have is velocity. All right, so we know from chapter 2 that velocity means nothing more than speed, right? So we have a speed that we have to consider. We have a wavelength. It travels in waves, so we have a wavelength. We have an amplitude, which for this lecture, amplitude is probably the least important of the four. And we have frequency. Okay, so I'm going to simplify velocity. What are we talking about? We're talking about electromagnetic radiation. What are your types of electromagnetic radiation? The most common to you is okay. We got X-rays and gamma rays, but
Light.
Exactly, light, right? So all electromagnetic radiation travels at the same speed, and that speed is the speed of light. All right. So how do we represent mathematically the speed of light? Light is constant, right? I always say it's constant. It's really kind of edgy. That's a shocker, isn't it? It's constant within a medium. Okay? You put a straw into your cup of water, what do you see? If it's clear cup. So it looks like it breaks, right? And that is because the speed in the different medium between the air and the water is a little bit different. It's only slightly, but it's a little bit different, right? But once it enters that medium, it's constant. And what that constant means is that if you were to put a flashlight on the front of a space shuttle and shoot the space shuttle across the atmosphere, the speed of light is still going to be the speed of light. It's not going to speed it up. Even though you got it on the front of a space shuttle, it's going 40,000 miles an hour. It's not going to be speed of light plus 40,000 miles an hour. It's going to be speed of light. Okay? So you're not going to speed it up. You're not going to slow it down. It will alter a little bit in a medium, right? But everything does. Sound travels faster the thicker the medium. Underwater, sound is something like 1,000 miles an hour. Outside at sea level, it's more like about 750. All right. So light goes opposite direction. Might slow down just a little bit in a medium. The recognized speed of light in vacuum. All right. So it all travels. I'm not going to ask you all that. All right. So it's the speed of light. Okay. It's the speed of light, and that was just to make you understand what the constant is and why it's constant. So velocity is speed of light. So amplitude has to do with, again, we've got waves of light, waves of electromagnetic radiation travel like this. It's what we refer to as sinusoidal variations. It's a big word for waves. All right, so it goes up, it goes down, it goes up, it goes down, it oscillates. So if we were to take this and we were to just kind of draw a line across it, you can call that line, 0 point, resting mark, whatever you want to call it, doesn't really matter. So the amplitude is the measure of the height of the wave. So it's from this point all the way up to the top of the wave, or since it's going right across the middle, it would be from that point to the bottom of the wave. And really the amplitude, the only thing amplitude tells us is the intensity of the wave. So the brightness of the light, pretty much. So how much, purple light do we have? Oh, let's see, ultraviolet, but how much red light, right? So the quantity or the amplitude or the intensity of light, brightness of light. So that's all I'm going to say about amplitude. The rest of the stuff is the more important things to grasp. Okay, so frequency and wavelength and velocity. Velocity is constant. We already established that. Now I want you to look at the wave equation on page 58. And look at the words, really, because if you look at the formula, it might scare you. Okay? So just look at the words. What does it say? Velocity, stop. What are we talking about? Speed, which is the speed of light. Right? So speed of light is equal to frequency times wave. All right. So velocity is equal to frequency times, I'm not going to use symbols, I'm just going to use frequency times wave. Speed of light is equal to the frequency times wavelength. All right. I'm going to draw a separate wave down here. I'm going to go all the way to the edge of the board over there. All right, so since frequency is not very, it speeds up and slows down, speeds up and slows down. All right, so before we get to there, let's define what these are. The words. What does frequency mean? How many times something happens, how often something happens, right? So frequency, how frequent do we meet? Well, 3 times a week. How frequent do you meet in clinicals? 2 times a week, right? So frequency is how often something happens. So it's how often we have a wave, okay? So we got frequency, how often? And the other one is wavelength. What do you suppose that means?
Of the wave.
The length of the wave, right? So here's the kicker on wavelength, though. The wavelength, the thing to keep in mind on wavelength is you've got to measure the wavelength at the exact same spot on 2 adjacent waves, right? So we're talking about a single wave. These are amplitudes here. We're talking about a single wave. So we've got, a point here, and the wave goes up and it goes down. This is one full cycle. All right. So that's your wavelength. It's the exact same spot on 2 adjacent waves. So it starts here, it ends there, and we start a brand new one there. So our wavelength is that, and it is the length of the wave. Okay? So frequency and wavelength multiplied together equals our velocity. Now, since we're talking about velocity being constant, it travels at the exact same speed. We don't speed it up. We don't slow it down. It always goes at the same speed. You're not going to be creating any X-rays in space. You're not going to be creating any X-rays underwater, right? So it's all going to be in the atmosphere here. It's always going to travel at the exact same speed, all right? So we can then, if that never changes, we could kind of substitute for this example and this demonstration, we could kind of exchange velocity or speed for time, right? So the same amount of time that it would take for X-rays to travel from one place to another would not change if the velocity doesn't change. Okay? So if we, shoot an X-ray from here to that wall today, it's going to take the exact same amount of time as it would take tomorrow, and the next day, and the next day, and the next day, because it's always going to be at the same speed. You following? All right. Then we're looking at this wave here. This wave, and let's assume that this wave is symmetric. If I were to take, let's do two waves, actually. Let's do one. This has got a lower amplitude. Yeah. It's got a lower amplitude. And it also spent a little time at the bar, apparently. So it's got a lower amplitude. That's fine. We got two different waves. Of these two, first off, which one has the longest wave? Top or bottom? Bottom. Right. Okay, so longer wavelength, shorter wavelength. We've got our time established as a substitute for velocity. Now, if I could take these two and just ignore what comes out behind me and just pay attention to kind of what's going on in front. But if I could take these two and I could shove them off the end of the board, right? Which one is going to be going off more frequently? The top one or the bottom one? The top one, right. So as frequency, let's do this. As wavelength increases, what happened to our frequency? Decreases. Right. So what we see in a wave equation is velocity never changes. As frequency, if we increase frequency, then we have to decrease our wavelength, or the wave, we're not going to decrease it, it's naturally going to decrease. So what can we say about the relationship between frequency and wavelength? Is it direct, meaning one goes up, the other goes up? No, it's indirect, and we have a different word for that we're going to use, and we're going to say it's inversely proportional. As one goes up, the other goes down, and it goes down by the exact same amount that the first one goes up. Okay, everybody with me? So, anytime I can simplify an equation, I will. It just, there's no reason to overcomplicate it and actually put speed of light in there and then word frequency and wavelength. There's no point to it. So what we're going to do is say 1 equals 1 times 1. Is that a true mathematical statement? Yes. Mathematical equation. 1 times 1 and indeed equals 1, right? So is this going to change? No. No, because it is constant at the light, right? So if I were to maintain my constant as I increased my frequency, what would I have to do with wavelength? Decrease it, and to make this a true statement, what would that be? 1/2, right? Is that yes? Yeah. If I flipped it around, what would I have to have now? 2, right? So as one goes up, the other goes down. They're inversely proportional. It's kind of like the inverse square law, right? As one goes up, the other goes down. It's inversely proportional. As one goes up, the other goes down by exactly the same amount. Okay, so what we can say then is that these two are inversely proportional to each other, right? So as this goes up, that goes down. As this goes up, that goes down, right? Okay. So then, okay, any questions on that? So this is the part I always think this isn't going to go quite as well as what I hoped it would. I mean, do they do it again? No? Anybody lost on this? Okay. Cool. Good job. Okay, then the electromagnetic spectrum, we kind of took a look at that. I want to draw your attention to page 59. Bushong says diagnostic ultrasound is not part of the electromagnetic spectrum. If you bought the DeAngelis book, I don't know if this question is still in there or not. I love the DeAngelis book. It's got 5,000 or so questions, multiple choice, primarily multiple choice questions. And, you know, we don't give much except for multiple choice questions. Your registry is going to be multiple choice questions. Highly recommend the DeAngelis and work through it. I've got corresponding chapters listed in the reviews for your DeAngelis. I take questions directly out of DeAngelis, and I try to put about 10% on your test to encourage you to use the DeAngelis to get you used to the, you know, multiple choice questions. Recommend you use it. But there are questions in there that are just flat wrong. And one of them that was in there, and it's few and far between, but there are some. And one that was in there for multiple editions, I don't know if he's taken it out or not, but one of them was, it said fundamentally the only difference between light and sound is frequency and wavelength. What is sound? It's vibration of molecules. Okay? Well, absent of molecules, you have no sound. There is no sound in space. There's none. Right? In the vacuum of space, there's no sound at all. And the only reason that our astronauts can speak to us is because we create an atmosphere inside of the, you know, rocket ships, space shuttles, inside the suits, things like that. They speak into radios, and the radios convert that signal to radio frequency, which is a type of electromagnetic radiation. Right? There's no sound in space, and that's the type of energy. Not even close, right? So if you get to something that just doesn't make any sense to you at all in the DeAngelis, look it up. You know, I really hope that they edited that one out because it was in there for probably 10 years, and people say, "Is this right?" No, it's not. Also, though, you know, I say that. Don't think a couple of bad questions in any book or misstatements or like in your Merrills, you might see an image that's flipped around. That doesn't make the whole book bad, right? It's just mistakes in the book. So anyway, I just wanted to point that out in case you ran across that. All right, so the energy of photon is directly, okay, that's what I wanted to add. Okay, so there's one other thing that I want to talk about. That is the energy. If you look on page 59, the energy of the photon is directly proportional to its frequency. All right, so when we're looking at the electromagnetic spectrum, what you see is energy, frequency, and wavelength. We've already established that frequency and wavelength are inversely proportional, right? But energy follows frequency. So if you look at the image on page 59, you see at the bottom of the page, you see very long wavelength in radio frequency, right? When I was taking physics, we actually calculated the wavelength of, there used to be a radio station in Dallas. It's probably still active. It's just doesn't play the same music. Probably doesn't have the same call signs, but it's what we call Q102. And it's 102 on your radio dial. And we calculated the length of the wave for that radio station. And it was probably about 15 feet long. Okay, so this is scale, all right? So this is not representative of what wavelength actually looks like. Radio frequency waves are quite long. So if the wavelength is quite long, frequency is very low. So if the wavelength is long, frequency is low. And if you look at the top, where you get to X-rays and gamma rays, what do you see in the wavelength?
Very short.
Very short. If they're very short, then the frequency is very high, right? So as you go up that scale from radio frequency through microwave, through infrared, through visible light, ultraviolet, and X-rays and gamma rays, what you're seeing is a decrease in the wavelength, an increase in frequency. and also increase in energy, okay? So don't confuse energy with, in your technique with mass. Energy in this case is gonna be more like your kVp and the energy level of your X-ray beam, okay? So, energy follows frequency, which means that energy is also gonna be inversely proportional to wave. They're gonna be the same. Okay. Did I lose anybody in that? Y'all good? Kind of quiet. You sure you're good?
She went over it in intro some too, so that
Did she?
helps. Yeah.
Okay.
Yeah.
All right, well, we're gonna pull up there and we'll talk, we'll review on Wednesday and then we'll push on. We've talked about visible light, radio frequency, and ionizing radiation. We'll talk about the different types of electromagnetic energy that we're most interested in, we'll have to deal with. Not really the same thing, we've got to talk about both of those things. And then we're going to press on into wave particle duality, which is, that's what, all right?